We have been discussing performance metrics of a clock and data recovery circuit, and we now have an understanding of jitter tolerance, JTOL, and jitter transfer, JTRAN. We have analyzed this for both the case with and without forwarded clock, and they are the same. Basically, you just assume that in one case you assume input data is jittery, and then find out at what point the bit rate increases beyond a certain value. For calculation, you just look at when the phase of clock drifts with respect to phase of data by a certain value. And jitter transfer is how much of the data jitter gets to the output. And the third one is jitter generation, JGen. And this has many components, random components, which is the phase noise of the VCO and the charge pump current noise and the resistor noise and so on. And then if you use a bang-bang phase detector, there is also the bang-bang jitter. There is some systematic jitter. This happens with any phase detector actually. This is due to pulsing nature of the phase detector. So this part, the second one we know. You just have to multiply the transfer function from these noise sources by the spectral density and you integrate to get the jitter. To understand the first one, we first need to understand what the phase noise of a typical VCO looks like, right? So that we will look at very briefly. I mean, this is a very fascinating subject in itself and there is a lot of papers on it. But we will do it sort of superficially and qualitatively, just enough to get an understanding of what the shape of the spectrum is, okay? And in this, essentially, if you make a VCO using transistors, and maybe they will have resistors also, and they have thermal noise at the very least, right? And the thermal noise causes a certain phase noise, that's what we'll look at. Additionally, when you use transistors, you may also have flicker noise, that will give you additional phase noise, but the thermal noise stuff will always be there, it's some fundamental thing. So that we will look at first, the phase noise of VCO due to thermal noise of the components. Now there are two main ways of making VCOs. One is an LC VCO and another one is a ring VCO or a ring oscillator. Fundamentally the phase noise looks the same in the two ways. The level of phase noise is different, but the shape of phase noise spectral density is the same. So we will look at both of these. They give you slightly different ways of understanding phase noise. First I will start with a ring oscillator. I assume all of you are familiar with what a ring oscillator is. The most commonly known type of ring oscillator is you have a chain of inverters, odd number of inverters, and you put them in a feedback loop. Okay. So now it will oscillate with a period which is related to the delay of the ring inverter chain. Okay. The most common one is the one using single-ended inverters, right? I'll show 5 here. Of course, you can use any odd number in a topology like this. And there are other types of ring oscillators where you can also use an even number. If you have a differential type, you can do that. Okay. So now what happens? Actually, if you look at every one of these waveforms. So let's say one has a waveform like this. So let me just show a rising edge at 1. Somehow the oscillator starts up, let's say, and because these are inverters, the output waveforms will go from 0 to the supply voltage. And we'll assume that when this voltage crosses the mid rail, every inverter will have a certain switching threshold. I'll assume that that's VDD by 2. Its output will start switching. Okay. So its output, because it's an inverter, it would have been high when the input is low, and then it starts switching here and it does that. And we'll assume the waveforms everywhere are identical. Okay. So this will be, if this is 1, this will be 2, and when 2 crosses VDD by 2 in the opposite direction, 3 will it will start switching up like that. Okay. This is 3, and 4, when this crosses like that, it will do that and so on. Okay. And then 5 will be when this one crosses, it starts switching, it will do that. And 6 is basically the same as 1. So essentially this one will come here, and at this point it starts switching down. And I mean, this happens cyclically, right? So little difficult to draw all the waveforms cleanly by hand, but you get the idea. Okay. So alternate waveforms are inverted, but they are delayed by a delay of each inverter. So what will be the period of the whole thing? What is the period of oscillation? Huh? So basically, if each one has a delay Td, what is Td now? Td will be the delay between when 1 starts rising and when 2 starts falling. Okay. So that is basically the delay between these two. And in this case, I mean, if you have n inverters, the period will be 2n times Td. Okay. Because it takes n to go through once for half a cycle, and then once more to reverse the polarity and complete the cycle. Okay. Or the frequency f0 is 1 by 2n times Td. Okay. So now let's see what happens in reality. So now for that, I mean, let's see what happens with noise, right? Now I'll break the oscillator loop and just consider the delay line, right? I have 5 inverters in cascade. So this is 1, and that is waveform number 6. What should happen actually as 1 rises, like that, right? And 6 will fall after how many? It will start falling after 5 delays, right? So it will do that. Okay. So the distance between these two this is 5 times Td, and the value of Td depends on the size of transistors used. Essentially, the way these waveforms rise and fall is by these transistors pushing current into the parasitic capacitor at that node. I mean the total capacitor at that node, right? So depending on the size of the transistor and the size of the parasitic capacitor, you will have some delay. Okay. Or in a current starved inverter, it is related to the current value and the capacitance. So let's not worry about how that comes about. So this is related to essentially the design of the inverter. Now what happens if you have noise? What do you think happens? So the easiest thing is to just imagine an input referred noise for each of them, or maybe for the whole chain. Okay. So imagine the input referred noise of this. What does it do? Basically, if you have some Vn over there, some noise, the actual input of the inverter is input minus Vn. Okay. So when that crosses VDD by 2 is when the transition begins for that stage. Okay. So this keeps happening. Basically, essentially there will be some noise. So because of that, the output transition, it doesn't begin here, it begins somewhere over there, and it can move around back and forth, right, depending on the noise value. The noise can advance it or also retard it. Nominally it will be 5 times TD, where TD is given by the design of the inverter. But if you look at how much delay is there between the rising edge here and the corresponding falling edge there, in every cycle they will be different, okay, just like any other random value. Is this okay? So now we also, because we are considering white noise, this will be different. Like let's say in the first cycle it does this, there will be some change in some excess delay, and in the second cycle it will be something different, and third cycle it will be something different, and these values will all be uncorrelated. Is this convincing? So this is the okay, this K is essentially twice per cycle. You have one for the rising edge, one for the falling edge. And this uncorrelated for different K, that is, let's say after a while I will make this fall and then go back, make it go back up again. So next time I will get a different value of tau. Okay, this is because the noise we are considering is white, right? So the noise produced at this instance is very different from the noise produced at some other instance, and they are not correlated. Is this okay? So what happens is, if I keep doing this, so let's say I will do that, then the output waveform, it was supposed to have done this 5 TD later, but because of noise it may do it a little bit earlier and something like that. Okay, every time it does something else. Okay, so the spectrum of this tau itself will be white because of white noise. Is this okay? Is this convincing or no? This is fine, right? Okay. Now what is happening in a ring oscillator? It's not as though here I am considering a perfectly periodic signal feeding the delay line. Okay, so at the input the edge locations are exactly where they are supposed to be. That is the distance between the rising and falling edges 5 TD, or the distance between two consecutive rising edges is 10 times TD, right? And there the output will have some jitter, okay, compared to the ideal value, and those jitter values will be white. Okay. Now what is happening in a ring oscillator? It's not as though I am driving this input by a perfectly periodic signal. Okay. So I will close the loop on itself. So what you can imagine is, so let's say I apply the first edge here from some external input, and then after the edges, after the input reaches the high level, I switch that off and then complete the loop like that. So what happens then to the jitter values? They will keep accumulating, right? Because now earlier the first edge was here, the next edge was 5 times TD later. Now the next edge is 5 times TD plus tau of 1 later. Okay. So that will, the input is moved by tau of 1, the output will move by tau 1 plus tau 2, right? Is this okay? And so the next edge is moved by the sum of first two jitter values. So the following one will move by the sum of first three jitter values. Okay, it is cumulative because this is an autonomous system, we don't have an ideal reference. So each input itself is jitter. So the jitter for the following edge will be the sum of jitter of all the previous edges. Okay, you assume some starting point. This is how it will look like. Is this okay? You first imagine that the first edge is at the ideal location. Okay. So you can imagine the same type of experiment. That is, you have an inverter line and then you have an externally applied edge going there. Okay. And once that edge reaches the high level, you switch it to the oscillator's output. Okay. Now you can also imagine that you have a million of these oscillators and you feed the same input edge to all of them. So the first edge is synchronized, right? The first input edge is synchronized to all of them. So then the next edge that comes back, they'll be different in each of these instances, right? Because of white jitter, they'll all be uncorrelated. And the next one will have the sum of the first two jitters and so on. Is this okay? So what happens is, if you run a million oscillators, with the first edge synchronized, the next one will move by some amount and the next one will move by some other amount and so on. Okay. So if you look at the timing of the first edge, it will have, as usual, some Gaussian distribution, and its variance will be some sigma tau square. That is basically the variance in the delay of a single delay line, right? That is, if you look at the delay between here and there, it has to be 5 times Td, but it will be 5 Td plus some tau because of white noise in the inverters. Okay. So this sigma tau is this sigma tau square is the variance of that jitter. Okay. So now what will be the variance in the next one? Next edge? It will be 2 times sigma tau square and so on. Okay. So if you look at the successive edges, they will keep drifting apart, right? So this you can kind of imagine. Let's say you take a million maybe mechanical wristwatches or any other type of clocks, you synchronize it today at midnight, okay, and then let them run, right? So maybe after the first day they will only be apart by seconds, and then you look at them after a year, they may be like completely apart, right? In fact, they could be apart by more than a day also, depending on how accurate they are to begin with. But essentially the drift between them, the variance of those clock readings will go on increasing with time. This is what you would expect, right? Because there is no other synchronization here, there is no other input, it's an autonomous system, and this is what happens. Is this okay? So if you look at this, because all these are uncorrelated, we assume white noise, the variances simply add up. Okay. So if you start with many oscillators that are synchronized, and then plot their variance, plot the variance of their edge locations versus time, right? It will go up linearly with time. Okay. This is sigma square, this is the jitter variance. Okay. Is this part clear? Now if you look at the variance of any one period or half a period, that will be constant, right? And that will be white, that will be uncorrelated between different instances. Okay. But if you, and also between different periods. Okay. But essentially the absolute jitter, which is the location of this edge compared to the ideal edge. Let's say you can also have a copy which is an ideal noiseless oscillator. So that will keep on increasing with time. Is this okay? So now because of this, what will the spectrum of something like this look like? What is the model for this? What is the model for the absolute jitter? What is the absolute jitter after k periods? it will be sum from 1 to k. This tau d refers to the change in the delay because of noise, right? Is this correct? So it goes up linearly as you progress through the edge positions. Okay. So now this we assume is white. Okay. So what will be the spectrum of that? What is the transfer function between this one and that one? And this is just a simple discrete time filter, right? What is the transfer function here? If tau d is the input and tau apps is the output, what is the transfer function? This is an accumulator, right? What is the transfer function of an accumulator? What will this be? Huh? Tau d. The way I have written it, it is tau d of k. Okay. So this essentially says that if you write the transfer function, it will be this times 1 by 1 minus z inverse. Okay. So I won't go through the quantitative calculations and getting all the scaling factors right and so on here. It can be done. That is, you can first of all find this tau d as a function of the noise in these things, right? The amount of current you use and so on, using some models. And then from that you can get the from the noise you can use the slope and get the tau d, and from tau d you can get tau apps and so on. I just want to get the shape correct, that's all, right? So if this we know, this has a white spectrum, okay? What should I multiply this with? What should I multiply it with? Yes, Krishna Kumar, what is it? 1 by? So 1 by 1 minus exponential, what is it here? Minus j 2 pi f. Now it depends on the sampling interval of tau d. We assume that it is sampled in every half period. It's okay, actually it doesn't matter, because again we are only looking for qualitative results. So I'll just call this tau h, where tau h is the half period of oscillation, right? And what is this? This form appears in a lot of places, right? What will be the magnitude square of this? Yeah, so this can be written as exponential minus j pi f tau h times exponential j pi f tau th minus exponential minus j pi f th square, okay, magnitude squared of this. And this whole thing is basically j2 sin pi f th, okay. And when you take the magnitude squared, I mean the first part is just 1, okay. So the magnitude squared of this comes out to be 4 sin square pi f th, okay. And this also, so essentially this tau d is white from 0 to 1 by 2th, and S tau abs will have that shape, right? It will basically have this multiplier is basically 1 by 4 sin square pi of th, and for frequencies much smaller than the Nyquist frequency of the sampling, this can be approximated by the argument of sine is the argument itself. So this will be 1 by 4 pi square f square th square. Is this okay? So this the shape in particular at low frequencies will be of the order of 1 by f square. That's all that we need to know now. Okay. So if you look at it in the time domain, you start a large number of synchronized oscillators and look at the edge positions after that. You can compare them to each other, or you can compare all of them to some noiseless clock. What happens is after the first edge you will have some variance, after the second edge you will have double the variance, and so on. Okay. The variance goes on increasing linearly with time. Okay. And it goes unbounded, right? Because again, with the example of clocks, if you run two different clocks long enough, you can imagine that the difference between them could be in the matter in like seconds or minutes or hours or days also. If you run long enough, this is going to happen. Okay. So that will go off like that. And if you look at it, look at the spectrum of this, it's like passing a white noise process through an accumulator or an integrator, and the spectrum of that will be 1 by f square. Okay. So this is going off to infinity at f equal to 0. That is the same as in the time domain, you wait long enough and they will the difference between them will diverge to very large values. Okay. So this is the model of the phase noise that is very commonly used for an oscillator. Okay. So if you plot the phase noise of an oscillator, you know that basically it is just a scaled version of this, right? If you have tau abs, then 2 pi f naught, where f naught is the oscillation frequency, this is the phase. So you plot the spectrum of this, basically you plot the two-sided spectrum and take one half of it, that is the phase noise, and that's usually plotted on a log scale. And if you plot this 1 by f square on a log scale, you will get this line. Okay. Minus 20 dB per decade line. So again, I am only using like qualitative arguments. All our interest right now is just to be convinced that the shape of the phase noise of an oscillator is fundamentally 1 by f square. It may have other terms also, but fundamentally it will be like this. Okay. Okay. Now this is due to thermal noise, and this is again like a fundamental result, right? It doesn't matter how you make any oscillator, it will always have this type of phase noise, whether it is ring oscillator or LC oscillator or even something unrelated to this. You make mechanical oscillators, spring mass systems, or you make lasers and so on, all of them will have phase noise like this. Okay. In addition, a practical oscillator can have other terms, especially we are concerned with CMOS oscillators, and MOS transistors have 1 over f noise, right? So it will have white noise, that gives you 1 over f square type phase noise, and it turns out that this 1 over f noise will give you 1 over f cube. Okay. So again, that is not hard to imagine, because this tau abs is just tau d going through an accumulator. This accumulator has a magnitude square of 1 by f square, right? Now if this is white, you get constant times 1 by f square. If this is 1 by f, because of flicker noise of the components used in the oscillator, you get 1 by f times 1 by f square, so you get 1 by f cube, and that will be dominated low frequencies. So you will have some minus 30 dB per decade component on cube, sorry. And this may or may not be relevant, okay, meaning because as you know, in a clock and data recovery circuit, if you look at the transfer function from the VCO phase noise to the output, at low frequencies there is a strong suppression, right? It is going to 0. So this may or may not contribute to jitter, but it will be there. So you have a minus 30 dB per decade or 1 by f cube part of it, and this corner frequency is called f 1 over f cube corner frequency in an oscillator. Okay. And finally, as you go to higher frequencies, what happens is that there will be flattening of the noise. This 1 by f square indicates that it will keep going on indefinitely, but it won't do that. There will be some constant part. The reason this happens is very easy to imagine, at least if you imagine buffers, right? You assume a voltage controlled oscillator, and let's assume that here the phase noise is 1 by f square, but finally you will put this through some buffer. Okay, the buffer will have white noise, so that means that whatever the input edge is, the output edge should come a little bit after that, but because of noise there will be some jittering around, and because of white noise the jitter itself will be white. Okay. So finally, this will not keep, even if you go to high frequencies, this will not keep going down indefinitely. It will have a sort of floor. Okay. So it's easiest to imagine if you have an ideal oscillator with 1 by f square phase noise followed by a buffer. The buffer will add this type of stuff. Okay. Is this okay? So if you make an oscillator, a CMOS oscillator, and plug it into a phase noise analyzer, you will see a picture like this. Okay. You will have some 1 by f cube part, 1 over f square part, and a flat part. Out of that, this 1 by f square part is the fundamental phase noise of an oscillator which has white noise in it, and this floor can be because of external components. It will be there because finally you have to take the oscillator and drive something else, and for that you will use buffers. Okay. Again, whether that's relevant or not depends on the system. Then you will also have this 1 by f cube noise. This also may or may not be relevant. If you use the oscillator in a feedback loop like you do in a clock and data recovery circuit, this low frequency part can be very strongly suppressed, right? Because we evaluated the transfer functions, and where is that? So this is the transfer function from the VCO phase noise to the output, and you can see that at low frequencies there is a very strong suppression. Depending on where the 1 by f cube corner is, it may not become relevant at all. Okay, what may be relevant is from this part of it and that one. Okay, is this fine? Now, what will be the jitter contributed by the VCO? It is the phase noise spectrum of the VCO multiplied by this transfer function magnitude square integrated from 0 to infinity, right? So we can quickly do that for the 1 by f square part of it. Okay. The flat part of it, because it multiplies by this, that you have to integrate separately. Okay. And also this transfer function itself you cannot integrate from 0 to infinity, right? Because this will give you, this will diverge. Okay. So any questions about any of this? The oscillator phase noise? Yes? Yeah.
But when we are using it in the loop, the oscillator won't be fixed.
Correct. So that's why, I mean, you assume that you have a free running oscillator in a feedback loop. So then it will not be free running, and when you multiply it by the transfer function, it will remove that accumulative part of that. Okay? Because see, I mean, without the feedback loop, a free running oscillator, so again, let's say you imagine large number of them and you measure the variance in the edge positions after a long time. That will go on diverging continuously. But if you see now, you plot phi ck, right? You evaluate phi ck and you find the variance of that, that will not be infinite, that will not diverge. Okay? It will increase up to some point and then it will saturate. Okay? So that will be taken care of when we multiply it by the transfer function. Anything else? Now, okay, before I go to the calculation, let me show a similar calculation, calculation that gives a similar conclusion with the LC also. This is a tank, and this by itself of course has no loss, and if you apply an initial condition on it, it will keep oscillating forever. But of course every real LC tank will have some noise, and I will model it by a single parallel resistance Rp. Okay. Of course, in this case, if you apply an initial condition, it will die out after some time. And to fix that, what you do is, this is a GM, you connect it in positive feedback, like that. And this GM will have a characteristic, something like this. At low frequencies, the transconductance will be, at low amplitudes, the transconductance will be GM. This is Vi, and that is the output current. Okay. And it will saturate to, so let's say plus minus I0. Okay. So essentially you have a transconductor. Of course the transconductor is not going to behave linearly for over an infinite range. It will saturate to some current. Okay, so this is a typical model of an LC oscillator that is used. Now for it to start oscillating, this GM has to be greater than 1 by Rp. Okay, so imagine that there is a very small initial condition on the capacitor. Okay, so that the GM is also operating in the linear region. Then if GM is greater than 1 by Rp, what happens is you effectively have LC and a negative conductance, right? So you will have L, C, and you will have Gp, which is the conductance corresponding to Rp, minus GM. Now you start from some initial condition, the natural response of this will be an exponentially increasing sinusoid, and this envelope will be given by Gm minus Gp by C, exponential Gm minus Gp by C. Okay. Now of course it won't build up indefinitely, because at some point the amplitude will cross the saturation limits, okay, and the amplitude will get fixed. This is how a practical oscillator works, right? Because if you had a linear behavior forever, then this amplitude also will build up forever. Okay? It will be steady only if GM is exactly equal to 1 by Rp. In a practical oscillator, GM will be more than 1 by Rp at the operating point, and at some point there will be some saturation. So when the oscillation amplitude exceeds this value, right, it will saturate to some amplitude. Okay, and you can calculate the amplitude. You can assume that the voltage across, the typical way you also analyze an LC oscillator is, you assume that the quality factor of the LC tank is high. Okay, so that means that you assume that across this you only have a sinusoid at the fundamental frequency, right? So then you can go ahead with the analysis and find out the amplitude and so on. Is this okay? So that is for amplitude, and I don't want to get too much into that, or maybe we'll do it a little bit. Yeah, let's do that so that you have at least an idea of. Have you seen this before? How to calculate the amplitude in an LC oscillator and so on? Maybe not all of you have seen it. So anyway, you can calculate the amplitude. Now I will take a particular case. So, and do you understand why I assume that here I have only a sinusoid at the fundamental frequency? The assumption is because of this. What will the impedance of this look like between these two terminals, this network? What is it? If I plot, if this is Z1 looking into that one, mod Z1 versus omega, what will that look like? Notch. I see some of you doing this, some of you doing that. Which is it? Minimum at the resonance frequency. Maximum at the resonance frequency. Maximum at the resonance. The parallel LC, right? So if you imagine there is no RP, then the reactance of this and that will cancel and you will have an open circuit. With RP, what happens is that the impedance will be maximum. Where will it be maximum? Basically when j omega c, which is the admittance of the capacitor, exactly cancels the admittance of the inductor. So then these two will cancel out and become an open circuit. What will be the magnitude at that frequency? This will be RP. Okay. Now the quality factor of this, that is the width of this, right? That depends on the quality factor. And if you look at the 3 dB bandwidth of this, what will that be? What is it? Omega naught by the quality factor. Okay. Now let's imagine that the quality factor is reasonably large. Okay. So in that case, what happens is this bandwidth is small. So let's say if the quality factor is 10, so this spacing is only 1/10 of omega naught. Okay. So now let's imagine that, so we have a GM connected here, right? We have a transconductance connected here. Okay. And it can be injecting signals at any frequency. Okay. It's possible. But you can see that if with a high quality factor, it's only at this frequency that you have an appreciable impedance. Okay. So if you go a little bit further away from this, the impedance value becomes very small. So for a comparable current injected here, the voltage values at any other frequency will be small compared to the value here. Is this okay? So this is an assumption. I mean, if the quality factor is high, you can assume that to a first order, the voltage across this is just a sinusoid at this frequency. Okay. So you assume that it is Vp times cos omega naught t. Right. Now when you connect it in an oscillator, what happens is that the input to the GM is like that. Okay. It is a sinusoid according to our assumption. The output of GM will be, it will follow this linearly and then at some point it will clip, right? It will clip to either plus I naught or minus I naught. Okay. So what does the frequency domain representation of this look like? The current that is flowing out of GM. What will that be? Huh? Frequency domain. What is it? Huh? Why will it be slightly spread? Yeah, this is just if the input is periodic, input has a periodic with a frequency omega naught, the output is also periodic with a frequency omega naught, right? Only thing is it's not a sinusoid. So if it's not a sinusoid but a periodic signal, what will that spectrum look like? It will have a fundamental and its harmonics. Okay. So that means that the current injected from GM will have a component here at omega naught and at maybe If it is symmetrical, it will be at 3 omega naught and 5 omega naught and so on. Okay. Now you can see that if the quality factor is high, the magnitude of the impedance at 3 omega naught is so small that you can neglect the voltage at 3 omega naught. That's the idea, right? So in general, the voltage across this will be at every harmonic of omega naught, and that also can be analyzed. But for hand analysis, if you assume a high quality factor, you can only consider the fundamental frequency. Is this okay? On top of it, we can make one more assumption which will let us calculate the amplitude also quite easily, which is that, so I'll assume that the characteristic of the GM is like this. So we said it will have this saturation, okay. I will take an extreme form of it where I have essentially a current switch. That means that if this voltage is positive, it will push current in one direction. If the voltage is negative, it will push current in the, or pull current the same amount of current. Okay. So in this case, what will the current output of GM look like? So the voltage across the tank, V tank, will be something like this, right? And this period is 2 pi by omega naught. What I have drawn doesn't look much like a sine wave, but you imagine that it is. Okay. Okay. What will the current look like now? Huh? It will look like a square wave, right? It will have plus I naught and minus I naught. Okay. So now will you be able to calculate the amplitude Vp? So now the current from GM consists of the fundamental component and the harmonics. While calculating the voltage, we are neglecting all the harmonics because the voltage due to the harmonics is very small. So all we need is the fundamental amplitude of the current times the impedance at the fundamental. What is the impedance at the fundamental frequency? Rp. What is the fundamental component of this current? Yeah, the fundamental component of this current is four by pi I naught. Okay. So what will the amplitude be? 4 by pi I naught Rp. Okay. So you can easily calculate the amplitude in this case. This is, this is an aside, this is a sort of diversion from our phase noise analysis, but at least a very basic type of LC oscillator, and this actually models the reality quite closely. There is a type of LC oscillator you make by putting an LC tank and a differential pair across it. Okay, differential pair GM in positive feedback across it. That is not a bad approximation for this current switch. Okay, so this is in that sense it's also practical. Okay, this assumption is very commonly used in analysis of that type of oscillators. So you get the amplitude. Now to analyze the noise, you use some hack. This also can be done rigorously, but I will not do that. For noise analysis, I will have L, C and Rp, okay, and of course the noise here is generated by Rp, okay, and essentially what I wanted was to make this a sustaining oscillator. I need a negative resistance across it, right? I will assume that it is exactly minus Rp, because this is easy to analyze, that's all, without all that nonlinearity and so on. And the assumption is that it also creates a noise. The noise spectral density of noise due to Rp is 4 kT by Rp. It's assumed that a negative resistance also contributes the same noise spectral density, right? 4 kT by Rp. The resistance is minus Rp, but the noise generated is 4 kd by Rp. Okay, Rp is of course positive here. Is this okay? So now with these currents you try to find the voltage across this, noise voltage across this. What will that look like? I just have to multiply this total spectral density 8 kT by Rp by what? What is the impedance of this whole network? Rp will cancel out, right? Rp and minus Rp cancel out to give you an open circuit. So all you have is 1 by j omega L, or rather minus 1, so impedance, right? So the impedance is 1 by j omega C minus, plus 1 by j omega L square. Okay. So we can continue this, but what will this look like actually? If I plot it versus frequency, what will the noise spectral density look like? What will this look like? Huh? Notch. Why a notch? I mean, this is again, you are multiplying some constant by the magnitude square root of the impedance of this, right? What is the impedance of this? Huh? Yeah, but I mean, in this case, it's not going up to Rp, it will go up to infinity. Okay, so it will look like that. Okay. So now this is just the noise here, right? Noise at this at these nodes. Now earlier, if you recall, again you can do quantitative analysis with this. I am not very interested in that. If you recall our earlier discussion of jitter, if you look at the total noise in a periodic signal but with some jitter, you will have an impulse at omega naught and you have sidebands next to it. The relatively, if you measure relative to the strength of the impulse, the sidebands are the phase noise, right? So you can see the phase noise again, we can derive that. If you derive this, basically, if this is omega naught and if this is omega naught plus delta omega, this will be of the form of 1 by delta omega square. So again giving you this 1 by f square for phase noise. Okay, so we can do that in the next class. So the ring oscillator picture is useful to understand the cumulative nature of phase noise. It's actually quite easy, right? Because like in each cycle the delay line adds some delay and then this goes on accumulating. Okay, sorry, in each cycle the delay line of course has a delay, but in addition to that it has a jitter, and the jitter in different cycles are uncorrelated, so it goes on accumulating. So 1 by f square is very easy to understand in that case, but even in case of the LC oscillator you can do that, right? So the point is, whether you have LC oscillator or a ring oscillator, the phase noise will have this proportionality to 1 by f square. Okay. So using that we can calculate the jitter generated due to a VCO. Is this fine? Any questions? Okay, we'll continue from there. Just think about this, how we derive these things and so on. I'll confine myself to this type of very qualitative discussions because this is very interesting, and if we go on doing it, we can keep doing it forever, the noise analysis of oscillator. But for us, main thing is to know that it has this shape. Okay.